Alright, let's talk about capacitors in circuits, physics fans. So, capacitors, first we want to examine what a capacitor is and what it does. So capacitors are generally parallel conducting plates, at least simple ones. At least simple capacitors are parallel conducting plates, and they store charge. The point of them is so you can put charge on them to hold for later, or sometimes you get charge out real fast in a spike. Yeah, so there's a lot of things to do. That's kind of the basics of them. So you could, if you attach this to a battery, the current, which we actually define as the way a positive would flow, is going to flow away from this one and towards, well, let's see. So the positive is going to go, positive is going to go that way. So we're going to put positives on here, and we're going to take negatives off and put them here. But in reality, what's really happening is you are having electrons, you're pushing them onto this plate and pulling them off of this plate. So you're going to get a positive plate here and a negative plate here. So we should know that both plates have the same magnitude of charge, meaning that as many electrons as you put on here, you're going to pull off this side. So we can define capacitance as Q over V. So the amount of charge you can put on each plate divided by the potential difference applied by the battery. So like that, where you have, so it's important it's not just the battery, because once again, if I put like some resistors in here, well, put resistors in here, wouldn't affect it unless I like wrote it in parallel. But if I put like a parallel resistor in here, that would affect it. So it's the amount of charge on each plate and the potential difference across the capacitor. Okay, I shouldn't say the resistors wouldn't affect it. It would affect at the time, but it wouldn't affect it in the steady state. Okay, so once a capacitor is fully charged, you've put as much charge on one plate as you can, taken as much charge as you can from the other one, and then current in the circuit will cease flow. So let's look at another circuit with a resistor in there this time, so we can actually do some more realistic math. So if we have this circuit, what we can do is we can try, if we want to try and figure out the initial or final current or something, well, the final current is going to be 0. If we want to try and figure out the initial current or as a function of time, we can do that. So we can take this equation we have up here, and we can say that Q equals CV is another way of writing that. All right, but what's V? Well, I'm glad you asked. V, initially, if we pretend the capacitor is not there, because initially the capacitor has 0 resistance. Let's write that down too. So initially an uncharged capacitor has no resistance. So my initial current is actually going to be entirely moderated by the resistor. So I can actually just say, since the capacitor has no resistance or impedance, it's kind of a better word here, but that's not really on our curriculum. So I could say current equals V over R, right? And just solve that way. But what is it as a function of time? Well, what's going to happen as the charge builds up, that's going to create an electric field in my capacitor, which I think you guys have already studied recently. So as I'm putting positive charges on one plate and negative charges on the other, it's going to create an electric field and therefore a potential difference in my capacitor. And we can define that, put values to that if we needed to. And so if put more charges on there and my potential difference grows, that means that there's less potential difference across my resistor. So I'll graph it now, and I'll prove this graph in a second. But the potential difference across the capacitor, I'm going to call it VC, as a function of time, is going to increase. And it's going to look somewhat like that. And it's going to asymptote to some value. Okay, so let's figure out how to prove that. Well, once again, if I know that we're actually going to have to use Kirchhoff's loop law here. So I know that 0 equals plus V minus IR minus Q over C, right? So there's a couple of things we want to remember with this. We want to remember that current is the rate of change of charge. So I'm going to write it like this, and then I want to solve this differential equation, which I substitute this in. So it's going to be 0 equals V minus R dQ dt minus Q over C. So generally speaking, when you solve differential equations, you want to take this differential term and put it by itself. Now this is just a first order, so this isn't too bad. So let's do that. So let's say R dQ dt equals, put that over there, so Q over C minus V, right? So now I'm going to divide by R, so let's just do that in one go, and divide by R, and we'll cross this guy out. So now, if you guys already know how to do this from math class, you can just skip ahead a minute or two. If you guys don't remember, I'll walk you through the process, at least the one I use, because, I mean, obviously it's the easiest one to me. So what I like to do is I like to do U substitutions, because U substitutions are great. So I would like to say that U equals Q over RC minus V over R, which means then that du will equal dq over RC, right? Because this doesn't depend on U, so I don't do it. So, and I know that you might look at this and say, oh, well, this changes and stuff, but this is the voltage applied by the battery. Maybe I should have called it EMF, but that's going to be constant. Okay, so now what I like to do next is just solve for dq. So that's going to be RC du. That way I can just plug it in over here. So now we've got, plugging this value in here. I've got RC du dt equals U. And now I can set this up like du over U and solve it like a natural log. So that's going to get me du over U is equal to 1 over RC dt. And yeah, just checking to make sure it's looking okay so far. So when I integrate this, I'm going to get natural log of U is equal to T over RC. If I raise both of those to the E, I'm just keep going over here. I like to go down normally, but I don't want to use up all my paper. Make it harder on the video. So that's going to be U equals E to the T over RC. And I feel like we've made a sign error somewhere. Let me check. We definitely have made a sign error somewhere, because these are both the same sign, which means they can't both be the same sign once I've moved one to the other side. So if I move this to the other side, I should have had V over R minus Q over C. So let's do that, and put it there, which means that minus R over C. So I should have, if I say U is equal to that, yeah, we're looking good. So I should have minus RC over here, and so 1 minus this and 1 minus that. So why did I know I made a mistake? Well, I knew from the concepts, I knew this graph was supposed to asymptote. And if I had that as a positive exponent, it's not going to become an asymptote. It's not going to behave the way I want it to. So I realized I had to have a minus sign there. So let's talk about another small mistake I've made. What would Mr. Akyalchin yell at you for here? Because we did an indefinite integral. That's right, plus C, but we've already used the C, so I'm going to say plus K. And so it's going to be plus K up here. And if you'd like, you can take this E to the K and bring it down and say you have U times some constant. We'll call it Q naught, let's say. e to the minus t over rc. So I need one final step. I need to replace this u with what u is. Actually, let's not call this q naught. Let's just call this k prime. So I get q over rc plus v over r is equal to k prime e to the minus t over rc. I want to solve this for q real quick. And I'll just do that. Alright, so when you solve for q, you cancel this r on bottom, and you end up with cv minus rc k prime, e to the minus t over rc. Well, I know that at time, if time is infinite, right, it should charge to q. So, which, by the way, cv, we can write that as q, or q naught, q max, let's say. So, and then, so I'm going to call that q max. And then what's going on over here with this k prime? How do we get that? Well, what is it at time 0? At time 0, it shouldn't have any charge. So if I put 0 in here, I just get rc k prime and q minus that. So I need this whole term to be q max also. So I'm actually going to say 1 minus, factoring the q max out, minus t over rc. And an important thing to note is that when it refers to your time constant, it might say tau, which is your time constant, and that's going to equal rc. So you could also write this as q as a function of t is equal to q max times 1 minus e to minus t over tau. Make it so you can see the rest of that. Alright, let's call that into this video. I hope you guys learned something, and I'll see you next time. I enjoyed physicsing with you guys.